In this lesson, we're going to talk about transformations on exponential functions. So, for this lesson, you're going to need to think back to earlier in this course when we learned about transformations. In the previous lesson, we learned about f of x equals c to the power of x, or y equals c to the power of x, being an exponential function. Just like in the first and second units we worked in, where we used parabolas or linear functions or radical functions as our basic graph, exponential functions are now another kind of basic graph that you've learned that you have to be able to do transformations on. So, just as a quick reminder, here is the format for these transformations. Remember, A and K both represent vertical transformations. So A, I'm just going to write it up here, is a vertical stretch, and K is a vertical shift, so up and down. Here inside, B is a horizontal stretch, and remember, when we're dealing with horizontal transformations, they always do the opposite of what they look like. So if the B value is 3, it's actually a stretch by 1/3. And the H value is a horizontal shift. And again, these do the opposite of what they look like. So if it's -5, it's actually a shift 5 to the right, even though it looks like it should be to the left. So using what we know about those transformations, we can do transformations on these exponential graphs. So here we have 2 to the power of -x and -2 to the power of x. I should have noted up here also, remember, this is a vertical stretch, but also a reflection. And same for the B value. So those can also be reflections, which is what we're dealing with here. So this first one is a horizontal reflection, and that means that the points x, y become -x, y. So what I've done here is I've drawn the graph of y equals 2x. I have the point 0, 1, the point 1, 2, and the point 2, 4. That is plenty of points for doing these transformations. In fact, oftentimes we'll only use 2 of the points. So you can see in my table of values here, what I've done is I've got my points for, yes, I've switched my x values. So when you have your point, I'm actually going to just write this a little bit differently. 0, 1, it's going to become or stay 0, 1. When I have the point 1, 2, which is on this basic graph here, it's going to become -1, 2. So this point here stays, this point here reflects. So you can see here when I do the same thing with the point 2, 4, the x value changes, so it becomes -2, 4. And I do something similar with these fractional amounts. X is -1, y is half, becomes 1, 1/2, and same with a quarter. As I said, these 2 points here are pretty much adequate for doing these transformations. Now the same thing happens when you work with the vertical reflection, or -2 to the power of x. Again, we have our point 0, 1, and our point 1, 2. And in this scenario, the y value is just going to change signs. So 0, 1 becomes 0, -1, and 1, 2 becomes 1, -2. So 1, 2 becomes 1, -2. And again, all these points just reflect downward. What you'll notice here with our horizontal and vertical reflection is that the asymptote has not moved. So for our purposes, you can almost ignore these little table of values. It's simpler just to look at point by point what's happening instead of actually plugging numbers into here, which is what I've done in the table. Okay, if we go down to the next example, here, again, the base graph here, you have to look at what your base is. Here we have a base of 2. So we're starting with y equals 2 to the power of x, but then we have minus 1. That's a k value, meaning I'm moving down by 1. So I've taken the point 0, 1 and moved it down 1, the point 1, 2 and moved it down 1. Again, if you wanted to, this is the point x, y, becoming x, y minus 1. So the point 0, 1 becomes 0, becomes 0, 0. And the point 1, 2 becomes 1, 1. So you can see those points there. Now the thing to notice here is that the asymptote moves down 1. So with vertical transformations, your asymptote will also move. Basically, if you're doing a shift up or down, your asymptote will move. Nothing else will really move that asymptote. If we go over to the next example here, you'll notice that the base here is 1/2. So the graph that I've started with is the graph of 1/2 to the power of x. Sorry, that's the one in pencil. So here, the graph of 1/2 to the power of x has the point 0, 1 and 1, 1/2. If I look at the transformations here, you'll see it's minus 1 as a h value, which means I'm actually going to the right by 1. So the point x, y becomes the point x minus 1, y. So here, this becomes negative 1, 1, and this becomes 0, 1/2. So these points have moved over by 1. If you look at the bottom here, for domain and range, our domain for both of these is just XER. Our range here, y is greater than negative 1. It will always be y is greater than or less than the asymptote. This, our x and y intercepts are 0, 0. This graph has no x-intercept, and it has a y-intercept of 0, 2. So you can find those characteristics after you've done the transformations. Examples C and D get just a little bit more complex. There's a few more transformations happening here. I'm going to start with example C. So example C here is y equals negative 3 times 2 to the power of x. So again, the first step is determining your base graph. The base graph here is y equals 2x. So you'll see I've got the point 0, 1 and 1, 2. Now, in this graph, I have a vertical stretch by 3, and I also have a reflection. So that means my point x, y is becoming x, negative 3y. So you don't really need this point here. That's an extra one, negative 1, 1/2. If you even just use these 2 points, 0, 1 becomes 0, negative 3, and 1, 2 becomes 1, negative 6. So here, I've got the point 0, 1, which becomes 0, negative 3, and the point 1, 2, which becomes 1, negative 6. It would be all the way down here. If you wanted to, you could include this point, negative 1, 1/2, which becomes negative 1, negative 3 over 2, gives you 1 extra point. This graph has not moved up or down, so that means that the horizontal asymptote at y equals 0 stays the same. My domain is XER. My range is that y has to be less than 0 now, since the graph is below the asymptote. There's no x-intercept, and the y-intercept is at 0, negative 3. If we look at the next graph, this one's a little bit tricky. In this graph, again we have a graph y equals 2x as the base. Now up in the exponent, remember that we always need to factor out our b value. So you can see here, I first just switched these terms around, have negative x plus 1, and then I factored out the negative. What this means is that this graph is reflecting horizontally, since the b value is negative, and it's moving to the right by 1. So again, I have my base graph, 0, 1, 1, 2. Again, I included that point, negative 1, 1/2. And my x value is becoming negative and adding 1. So negative 1, change the sign, it's positive 1, plus 1 becomes 2. The y value is unchanged. Again here, 0, change the sign and then add 1. So 1, 1, and 1, 2 becomes 0, 2. So you can see here, this point is reflecting over and then moving to the right by 1. This point is reflecting over, which doesn't do anything, moving to the right by 1. And this point down here would reflect over and then move over by 1. So this pink graph here is what the graph looks like. Again, the domain is XER. The range is that y is greater than 0. That's an error. Please change that in your notes. There's no x-intercept, and the y-intercept is 0, 2. This next example has a whole bunch of transformations in it. So we have this really messy thing here. Again, your first step is always to determine what is the base graph. The easiest way to do that is to remember that you could have an a value in front, you're going to have a power, and you could have a k value at the end. So here, the base graph is the base that's right with the exponent. So again, it's y equals 2x. The negative means that we have a vertical reflection, or a reflection over the x-axis. The 1/2 is a vertical stretch by 1/2. The negative 4 is right by 4, and the negative 2 is down by 2. This is where having the points is really helpful, because doing all of these in one step is quite tricky. So xy, here I have 3 points. I included negative 1, 1/2, 0, 1, and 1, 2. My x value is just going right by 4, so plus 4. But my y value is being multiplied by 1/2 and subtracting 2. So here, I'm going to multiply by 1/2 and then subtract 2. So you'll see I get these decimal values, which is totally okay. Also, because I'm going down 2, the asymptote will move down 2. So don't forget to move that asymptote. Drawing that asymptote in the correct place is super important because it allows you to determine the shape of your graph. So you can see here when I connect these dots and I go and approach the asymptote, I can see that this is the exponential shape of my graph that's just been flipped over and moved. And finally, in example 4, it's asking you to write an equation. The real estate board in a city announces that the current average price of a house in the city is $400,000, and it predicts that the price will double every 15 years. So this is very similar to an example that we did in the first lesson. We start with our initial value and multiply it by the growth rate to the power of time. In this case, it says it's going to double every 15 years, so we need to take however many years have passed, but divide by 15 before plugging it in. Now, if we wanted to think about what this graph would look like, we would have a vertical stretch by 400,000 and a horizontal stretch by 15. So we could think about what this sort of function that represents a real life context could actually look like as a graph.